Good day, one and all. This video is being made to explain organic chemistry to heterocyclic compounds as taught by Professor Ayinsu. Now, the only question in this video is that it is a supplementary material, not an alternative material to what is being taught at lectures. Then we are being reminded that this material is being done by the HESA academic board. And so if you have any issue at all, you can see any member of the HESA academic board. Thank you very much. So we start. Now, by the end of the lesson, these are the things that we have to know. So we just start right into it. Now, we are saying that heterocyclic compounds are organic compounds that have other elements apart from carbon in the ring. Now, I think in first year, we learned a lot of things around it, that we have homocycles and heterocycles, right? Now, homocycle will be a ring, a cyclic compound that contains only one atom. And an example of a homocycle, a typical example of a homocycle is a carbocycle. So benzene is a carbocycle because it has only carbon atom, right? And then we went ahead to see that there are heterocycles. Sometimes we don't have just carbon. We don't have just one atom, but we can have 2 or 3 or more atoms in a single compound in a ring form. And for those compounds, we call them heterocyclic compounds. So now the next point is that heterocyclic compounds can contain other elements such as nitrogen, sulfur, oxygen, phosphorus. There are many heterocyclic aromatic compounds, and many are very common. Now, the next term here introduces us to a different aspect of heterocyclic compounds. Now, heterocyclic compound will just be any cyclic or ring structure that has 2 or more elements inside. But then when we talk about heterocyclic aromatic, that means it will be some rules. You understand? So we have narrowed the narration down, and then with time we'll talk about what we mean by heterocyclic aromatic compounds. Now we are saying cyclic compounds that contain only carbon are called carbocycles, not homocycles, right? So if you are talking about only carbon, it's carbocycle. But if you are talking about a cyclic compound that has only one atom, then it's homocycle. And nomenclature is specialized. We will talk about nomenclature in no time. Why heterocyclic compounds? And why are we studying heterocyclic compounds? So the application of heterocyclic compounds provides a useful tool for modification of solubility, lipophilicity, polarity, hydrogen bonding capacity of biologically active agents, which results in the optimization of the absorption, distribution, metabolism, and excretion or toxicity or toxic properties of drugs or drug candidates. So these are like importance of heterocyclic compound, or why we are studying them, and it's very important. That is why I'm not skipping them. Now, what drugs are heterocyclic compound? A lot of drugs, right? The most famous are diazepam, isoniazid, promazine, metronidazole. It goes on and on and on, right? Now, we said furthermore, most of the vitamins, nucleic acid, enzyme, coenzyme, hormones, alkali contain, and these heterocycles. Very important. Now we are up to business. Nomenclature of heterocyclic compound. We are saying that heteroatom is to be counted as 1 or as low as possible. Very important. Now we'll do demonstration to illustrate. The next one is when there's more than one heteroatom, preference is given to oxygen, then sulfur, then nitrogen, before finally we give preference to carbon. And so we use this mnemonic, which is like old soldier never cry. So we first consider oxygen, that is in terms of numbering or even arrangement of the name. Then we'll talk about sulfur. Then we'll talk about nitrogen before carbon comes into play, right? Good. Now we are also saying that if I have NH bond, that is to say, in the ring, if I have nitrogen which is saturated, right, it will preside over nitrogen which is unsaturated, that is N double bond. That is what it's saying. Now we are saying that when there's more than one heteroatom, numbering should be as direct as possible from one to the other. Very simple concept. Now, substituents are numbered as low as possible, right? This is from the normal organic chemistry that we know. Now, we are also saying that acceptable prefixes include, now, if we are looking at oxygen as a heteroatom, we start the compound with oxa. If it's sulfur, we start the compound with tire. If it's nitrogen, we start the compound with aza. The truth is that if it's supposed to meet any other name that has a vowel, these last words will go away, right? So the oxa here will go, the A here for the tire will go, and then the A for the aza will go. So in so many examples, you realize that you see some of these ones going away. Now, the next point says that for partially unsaturated system, hydrogen, that's H, is used or are used to indicate the location of saturation. Very simple, right? Good. So we'll demonstrate that too. Now, this is a table which we have to pay attention to. We have to know the table. Probably in direct sense, we have to chew the table, because when we are asked to name the compounds, we will not be provided the table. We just have to know, the table, right? Now, this system of nomenclature is adopted, right, by IUPAC, so it's approved. Now, let's quickly go run through the table. So the table has ring size, saturated, partially saturated, or partly saturated, and unsaturated. Now, if the ring is three-membered ring and it's saturated, it has the name of Irene. And then if it's unsaturated, it has the name of what? Irene. Now, there's no partial saturation when we talk about three-membered heterocycles, so that is off. Now, if it's four-membered, we have saturated. It becomes ethane. And then if it's unsaturated, it becomes iti or it, anyhow you want to pronounce it, but in a sentence or in a word, it makes more sense. Then if it's partial, we can get dihydro. Dihydro in essence means that we get two continuous saturated points, right? So we can get maybe the second and then the third atom in the cycle being saturated. So we get dihydro, or maybe two other points, just two other points of saturation. Very important, right? Now it goes on and on and on. If it's eight-membered and is fully saturated, we have ocane. If it's unsaturated, we have ocene, right? And then in between, we will have the di, tetra, and hexa to show the points of saturated within the unsaturated or the partly saturated ring. Now, what we have to take note of here is that should the ring be partially or partly saturated, it will still take the suffix, it will still end with the suffix of what? Of the unsaturated compound. So if we have an eight-membered ring, right, which is partially saturated, it will still end with this one. That is all we are saying. It will still end with this one. So it would only end with this if it's fully saturated. That should be noted. Now let's run to the example. For each of the compound, there's a common name, but then we are learning the systematic or the IUPAC name. So now for the first compound, we have a three-membered ring. So the three-membered ring is either we are taking this or we are taking this, right? Now, the next consideration is that we have to look at the heteroatom. It's just one heteroatom, oxygen. Oxygen will start with oxa, right? And then it's fully saturated, so arene. So oxa plus arene. I said almost every time we remove this A, and so we have the oxirene, right? Oxirene, very simple, very straightforward. Now, the next one, we have a fully unsaturated ring. Now, the oxygen does not form double bond in a ring form because ideally it forms just two bonds. If it forms a double bond, it becomes a plus cation, you understand? So this is fully saturated ring. Now, for a fully unsaturated ring, right? Now, for a fully unsaturated ring like this, it has oxygen, it will start with oxa, and then it's five-membered. So five-membered, it has the suffix oli, right? Or o, how you want to mention it. And so we have the oxol. Very simple. Very simple. Now we go to more examples. So if we are moving on, yes. The next one is pyrrole. Now, pyrrole is partly saturated. That is because the nitrogen here can form a double bond. The nitrogen here can form a double bond. So it's partly saturated. And so when we have partly or part saturation, what we do is that for any point within the partly saturated one, we say still it will take the surface of unsaturated, right? It will take the ending of unsaturated, but then we'll use H or hydrogen to show the points of saturation within the unsaturated ring or the partly saturated ring. That is the idea. And so you realize that for the numbering, we'll start from here. This is number one. We say always we give priority to the heteroatom, number one. Now this will be number 2, 3, 4, 5, right? So you can go either way, it's the same thing. And now it has nitrogen, so it is aza. Very simple, right? Now it is partly saturated. Partly saturated, so it still takes this unsaturated suffix. Now we have the 1H here. The 1H here shows that within this ring at position 1, it is fully saturated or it is saturated there. Very simple. So now when we combine all, we have 1H azo. The A here will go away, as I said already, or as I've mentioned already. Very simple. The next one, we have the common name of the compound being piperidine, very common compound. Now the systematic name, we number. Position 1 here is a 6-membered ring. It's a nitrogen atom, so we have aza, and then it's fully saturated, so we have enene. Now for this one, we can omit the 1H and it will still be right. It will still be right because enene is only used when we have a fully saturated ring. So if it happened that the nitrogen here was not saturated, it would not have this suffix anyways, you understand? Yes. But then if you put it here too, it is not wrong. That is what we have to understand. Very important. Now the next one, pyrimidine. Pyrimidine, very common compound. Now in the case of pyrimidine, we understand that it has 2 nitrogens. We have to number. So we number from one to the other, said that we give them lower numbers. So I number from here 1, 2, 3, 4, 5, 6, right? So at position 1 and position 3, I have nitrogen atoms in the ring. So it's aza, but then it's 2 of the aza, right? At position 1 and position 3. So we put the 1 and 3 in square brackets, right? And then it's diaza because we have 2 of the nitrogens. And then it is a fully unsaturated ring, right? And so we have the surface for a 6-membered ring. Very simple concept. Very, very simple concept. So we move on. Yes. Now we have a lot of examples here to try. Let's quickly look at them and then move on. So the first example is an 8-membered ring. I mean, all the examples are 8-membered rings, right? So the first one we number. Always the numbering will start from the heteroatom. That is if there's a single heteroatom. So this is number 1. You can go either way, it's the same thing. Now it's a fully saturated ring, only single bonds. If we say full saturation, we are talking about just single bonds. It is only single bonds. So we can go with the okane, right? That is the suffix for 8-membered ring, and then it is aza because there's nitrogen in the ring, 1 nitrogen. So it's aza plus okane, that is azokane. Very simple. And the next one, we have 2 heteroatoms, oxygen and then nitrogen. Remember that we use old soldier never cry. And so if we have oxygen and then nitrogen, we give priority to the oxygen. So 1 here, 2, and then 3. We continue 4, 5, 6, 7, 8, right? So this is what we would have at position 1, there's oxygen. At position 3, there's what? There's nitrogen. Now, when we are now naming them to the same thing, the oxa will come before the aza, right? So the position 1 here will correspond to the first one, the 3 will correspond to the second one. Very simple. And the okane here is because it's fully saturated and it's 8-membered. And we get the okane from the table, right? And so if I'm supposed to go back to the table, let me quickly go back to the table. You realize that now for 8-membered ring, if it's fully saturated, we have okane. If it's unsaturated, we have ocene. So we are using okane in this scenario because the ring is fully saturated. Nice. Next one. We have an 8-membered ring is fully saturated. We'll still have the okane suffix. Now we have 3 heteroatoms. So we use old soldier never cry. Now, old soldier never cry. So we start from the oxygen, then we move towards the sulfur. So number 1, 2, 3, 4, 5, 6, 7, 8. So now position 1, position 3, at position 7, we have heteroatoms, right? So 1, 3, 7, oxa, tire, azokine. Very simple. Now, the next one, the narration changes a little bit because you realize that even though we have the same arrangement of atoms here, now the narration changed because there's an unsaturation here. Now, this ring is not fully saturated, neither is it fully unsaturated. So this is partly saturated, partly saturated. And so it will still take the surface of unsaturated ocene, right? But then for any point or any atom which is saturated there, we have to show it. So we number the same numbering. Number 1, 2, 3, 4, 5, 6, 7, 8. This is the normal numbering that we do. So oxygen is always 2 bonds, 2 bonds. It does not form 3 on a normal day, so we don't show that part, right? Now, the parent name, always I do the parent name first. The parent name would have 1, 3, 7 oxatire azocine, not azokane, azocine, right? Now we have to show the points of saturation. At this position, position 2, there's point of saturation. Now, at position 4, there's saturation. At position 5, there's saturation. And then at position 8, there's saturation. And so, because the 4 and 5 follow each other directly, we've made a 4,5 dihydro. It doesn't mean if you make it 4H5H, you are wrong. No, it's still accepted, right? So 4,5 dihydro. Then the other points of saturation is 2H and 8H. So that is also included. So we have 4, 5 dihydro, 2H, 8H, 137 oxathiazocine. Very simple, right? Now moving forward, we have the same parent ring as we had in this case. And so the parent name will not really change. It will not really change. The only difference here is that we have now saturated this part. And so the 4,5 dihydro is not there again because that point there is now unsaturated. We use the hydro and the H to show the point of saturation in an unsaturated ring, right? Good. So we will not show them here again. But then there are other substitutions available. On position 2, there's a phenyl group. Now on position 6, there's a methyl group. And so we arrange these two in alphabetical order. M comes before P. So 6 methyl, 2 phenyl, 2H, 8H, 137 oxythiazosine. Very simple, right? Now the next one, very simple, is only oxygen, right? Only oxygen. And then it's partially saturated. And so if it's only oxygen, we are looking at oxa. Now, if it's 8-membered unsaturated, we are looking at ocene, right? So oxa plus ocene, we remove this E from here, so it's oxocene, right? Now that will be the parent name, oxocene. Now we have to use the H to show the points of saturation within the unsaturated ring. So what are the points of, this is number 1. Now we can number to this side or we can number to this side. Just that we always number such that we give the lowest number to the substituent. And so we'll number to the side. 2, 3, 4, 5, 6, 7, 8. Now we can choose to go the other way and see what will happen. If I number 1, 2, 3, 4, 5, 6, 7, 8. The substituents will be at position 8 and then position 4. 8 plus 4 is giving me 12. If I go with the yellow numbering as I did here, the substituents will be on position 2 and then position 6. 2 plus 6 is 8. And usually I will go with the one that gives me the lower number. So I'm going with the yellow numbering, right? Yes, and so would have phenyl at position 2. We have methyl at position 6. And then we have to use alphabetical order to arrange the two. The other points of saturation that we have here is this carbon. On carbon 2 is only single bonds, that's saturation. On carbon 3, it's only single bonds, that's saturation. On carbon 8, it's only single bond, that's saturation. So we do 2 each, 3 each, and then 8 each to show that within this partially saturated ring, the points of saturation is the second atom, the third atom, and the 8th atom. Very simple. Very simple. Okay. Quickly, we move on. Yes, now aromatic properties of heterocycles. So now we are asking ourselves, what is aromaticity? Now, aromaticity is defined by properties. So the first property that we have written is that aromatic compounds are cyclic. Next one is that they are conjugated all around the ring. In other words, we are saying that they are fully conjugated. The next one is that the molecule must have 4n plus 2 pi electrons. So then the Hackle numbers are 2, 6, 10, 14, 18, right? That is what we have. Now, the Hackle rule states that all aromatic molecules must satisfy this condition. Very important condition for it to be aromatic. Then the last condition is that you should be planar or you should be flat, right? You should be planar or you should be flat. Now, there's another point that they have given us, and that is that pyridine has a lone pair, but it does not count it for the purpose of aromaticity, right? Which we'll talk about more when we go down subsequently. Now, there's a table to show us that meeting one criteria for aromaticity does not really qualify you. You have to meet all the 4 criteria. So we ask ourselves, are you cyclic? And so we realize that the second example here, it is not aromatic just because it is not cyclic. This one, it is not cyclic. That is why it is not aromatic at the end of the day. Right? Now, if we are cyclic as we can have in this, or we go to the next question, in no particular order, are you fully conjugated? That is, are you fully joined? Are your electrons delocalized around the ring? Now, if you have a no, as we have here, now this cyclopentadiene, it is not fully conjugated. This atom carbon here is sp3, and sp3 does not have an unhybridized p orbital to overlap and then form a molecular orbital for complete delocalization. So because it's not fully conjugated, it ceases to be aromatic. It cannot be aromatic. Then if you qualify as the next three have qualified, then we ask ourselves, how many pi bonds? Now the pi bonds are important because we are looking at the pi electrons, because your pi electron should fall within the range of Haeckel, right? And so we check your pi bonds. Now we know that for each pi bond, we have 2 electrons. But before we do the final calculation, we also check your lone pairs. Now we are not checking all the lone pairs you have, but we are checking the lone pairs that the compound have contributed to the ring as part of what? It's the localized electrons or the ring electrons. And so if we take the 3 which have qualified up to this stage, now benzene, the first one, it has 3 pi bonds, so it has 6 pi electrons, right? We will not conclude until we disclude the fact that it has no lone pairs. If it doesn't have lone pairs and then it obeys the Haeckel's rule, then we can say that, okay, it's aromatic. We have concluded. The next one, the same case, 3 pi bonds, no lone pair. It has a lone pair, just that this lone pair of pyridine is not contributed to the ring structure, so it cannot be counted here. So it still has the 6 pi electrons, and it's aromatic. The last one here has 1 pi bond, as we can see here. So that makes 2 electrons, and then it has an anion here. So it has electrons here, which it has contributed to the ring. So it makes it 4, but the 4 pi electron is not part of what? The Haeckel's rule. This is actually an anti-aromatic number. It's an anti-aromatic number, if we remember, right? And so it is not aromatic. Now, from this discussion, we should just be able to know when compounds are aromatic and when they are not aromatic. Some compounds are sneaky. They are not aromatic, but they will pretend to be aromatic. Next up, pyridine. Pyridine has already come in our discussion, and when we said that it does not contribute the lone pair, right? Now, pictorially, this is supposed to show us the electron cloud of pyridine to prove to us that it actually does not contribute the lone pair. So the red section here is where the blue here is the heteroatom, the nitrogen, as we can see here. And the red section here is the lone pair. And then you can see clearly that it's not contributed to the ring here. You understand? Now, they have also used this one to show you that this is the ring system of the electron. This is the 6 pi electron. And this has not been contributed. You understand? Yes, so it's aromatic, but then does not use the lone pairs as part of the ring structure. Very important thing to note. Now, if we look at pyrimidine, pyrimidine's case is similar because pyrimidine also has 2 lone pairs, 2 different lone pairs, but it contributes none of them. And so if you look at the red portion here, you see the lone pairs, they are outside the ring structure. So it has 6 pi electrons, but then that is it discludes the lone pairs that it has. Very important point to note. Very, very important point to note. Now we are still talking about pyridine. Now we are saying that the nitrogen lone pairs are not part of the aromatic system, right? We are saying that pyridine is relatively weak base compared to normal amines, but protonation does not affect aromaticity. Aromaticity, yes. So it's a very simple concept here that because the lone pairs here are not, it's not used as part of the aromatic ring. You understand? When it is protonated, as in this case, it does not really affect the aromaticity. But then again, they have mentioned an important concept that we cannot ignore, that pyridine is weak compared to normal amines. And so at a point, we have to explain why that is so. Now, there are 2 logical explanations that we can give, but then one of them is stronger than the other. Even though, so I'm talking about the weaker one first, then I will talk about the stronger one later. The weaker point that we can raise here is that the truth is that the lone pair here is not contributed to the ring. So it's not part of the primary reason why it's aromatic. But then this compound undergo resonance, which makes it more stable. And then when it's undergoing resonance in its normal state, it uses the lone pair here to contribute to the ring. And so if it's protonated here, it loses the resonance. And if resonance is making you more stable, no compound would want to undergo a reaction that makes it less stable. So that's a very weak reason that we can use, right? But then the stronger reason is the hybridization. Now, the nitrogen here is sp2 hybridized. sp2. sp2. The normal imine they are talking about, the NH2, the nitrogen here is sp3. Now, we have to understand the difference between these hybridization. We have to talk about something called the S character, because it is by understanding the S character that we can quickly, yes, S character, that we can quickly understand why this is so. And so now for explanation's sake, what we have to bear in mind that the S orbital is small and is closer to the nucleus. The nucleus has positively charged protons, right? And that attracts the electrons on the outermost shell. In this case, I'm talking about the lone pairs of electrons, right? Good. And so if your S character is high, it means that these lone pairs of electrons are closer to the nucleus, right? Such that there's a higher attraction of the positive center on the electron. And hence, it is difficult for you to donate it to act as what? To act as a base. Because a base is also electron pair donor, according to Lewis' definition of base. Now, if you have a lower S character, it means that your lone pair is not so close, as in this case, it's not so close to the nucleus relatively, and so it is easier for you to donate. Now, if you check the S character for this one, sp3 is 25%. Now, sp2 is 33.3%. And so you realize that because of the higher S character in the sp2, right, it has the lone pair has a higher pull, right? It's pulled higher by the electrons. Now, because it is pulled to a higher extent by the protons inside, that is why, yes. And so in summary, what we have to understand here is that the nitrogen in pyridine is a weaker base compared to normal amine, because the nitrogen in pyridine is sp2 hybridized. Now, sp2 hybridization, and then the nitrogen in normal amine is sp3. The nitrogen in pyridine has a higher S character. That means that the lone pairs are more pulled by the nucleus compared to the lone pairs on the nitrogen, the normal amine. And hence it is difficult for it to be donated relative to what? To the ones in normal amines. As simple as that. That is all. And that is the stronger point that we can give. Let's move on. Pyrrole. Now, pyrrole is a 5-membered heterocycle with 1 nitrogen. The pi electron system is similar to cyclopentadiene anion. That is true. Now, the truth here that the only thing that we have to know with respect to pyrrole is that it has 2 pi bonds, that's 4 pi electrons, but then the lone pair on the nitrogen has been contributed to the ring. Because it has been contributed to the ring, it has made it 6, right? And so you realize that if you look at this very well, it has the lone pairs are here, right? And it's part of this. So we'll have 6. Now, the next example that we have here is imidazole. Imidazole has 2 nitrogens, right? One of them has their lone pairs being donated to the ring. Now, this one is taking position 1 because NH takes precedence over N double bond. We have already talked about that when we were talking about the normal naming stuff, right? And so this one, we are just showing you that this is aromatic. Now it has two nitrogens. It is this nitrogen whose lone pair has been donated to form part of the ring structure. Now this nitrogens, the second nitrogen here, that's on position 3. The lone pair is not part of the ring. The lone pair is not part of the ring. Because the lone pair is not part of the ring, now it is more available to be donated to act as a base compared to this one. It's a very important thing that we have to take note of, because in the next example, they will ask us that question, that which of the nitrogens in, so let me just go to that section. They will ask us which of the nitrogens here. Now, because we already understand that this one is donated to the ring, we will not touch it. It is this one which is available to act as a base or to be given to form a coordinate covalent bond with a proton. Very important point to note. Now, the other point that we skipped that we have to run through quickly, that is, yes, we've talked about this. Since lone pair of electrons are part of the cis pi electron aromatic ring, protonation destroys aromaticity, making pyrrole a very weak base. What we are saying is that unlike the case of pyridine, pyrrole uses the lone pair to contribute to the ring structure. So it is part of the ring structure. Because it is part of the ring structure, when we force it to act as a base by donating the lone pairs to form a coordinate covalent bond, right, it will lose the aromaticity. And aromaticity is what is making the compound stable. So when it loses it, it becomes highly unstable, because no compound in the world will want to go to a state of instability. Now, it is a very, very weak base, because when it acts as a base, it loses the stability. You understand? So that is the whole thing around pyrrole. So compared to pyridine, pyrrole is a very, very weak base, right? Good. Now, nitrogen heterocycles. So these are heterocycles that occur in nature. Cytosine, thiamine, uracil, histidine. Drugs with nitrogen heterocycle, we have metronidazole, flumazenil, or the other cimetidine. Yes, we have quinine here, and very important. We have to take note of those ones. Now, pyrimidine and then purine. This discussion will take us a little bit into nucleic acid, because these are nucleic acid bases, right? These are categories of nucleic acid bases. Now, this is the parent structure. You have to take note of the structure of pyrimidine and then purines. The bases are actually modifications of this one, but they have the same nucleus. They have the same. And then we have to also take note of the numbering, right? Numbering, very important, right? So now, if you take a very closer look, you realize that pyrimidine is here. Now, in the purine, there's pyrimidine plus imidazole. So that's the composition of the purine. There's a pyrimidine ring here, and there's an imidazole ring here, right? That fuse to form the purine. Now, the nucleic acid bases, we have adenine and guanine. Adenine and guanine are the purines, right? They are the purines. And then we have the cytosine, thiamine, and then uracil. Now, they are the pyrimidine derivative, right? Yes. All of them are used in DNA or RNA, but then thiamine is for DNA and uracil is for RNA, but the other three you can find in both of them. Now, this is deoxyribonucleotide. Now, we have to first of all understand the nucleotide. That will be talked about in a different discussion. But a nucleotide would have a phosphate, a sugar, and then a base. The base, for the first example, the base is the adenine that we have here. Now, it's called deoxyribonucleotide. ribose because the sugar here is ribose sugar, just that at position 2, it has lost an oxygen. So deoxy, right? We have removed an oxygen at position 2. So very simple. So these are all examples that we can take note of. Good. Now we are at a different point. Chemical properties of heterocycles. Chemical properties of heterocycles. So heterocycles include many important natural materials as well as pharmaceuticals. So we have penicillin, J, phenobarbital. Now the list goes on and on and on, right? Now let's concentrate on 5-membered unsaturated heterocycles. So we have pyrrole, furan, and thiophene. Very common ones, right? So these are the ones that we'll talk about here. Now they are unsaturated, right? They are unsaturated. Yes. Furan. Now we'll talk about how to make furan, right? So we are saying that it's made commercially by extrusion of carbon monoxide from furfural, which is produced from sugars. And so with the pathway, we have pentose sugar. Now the pentose sugar is acidified, and then we get the furfural, and then in the presence of nickel catalyst and then heat, right? 280 degrees of heat, we can produce the furan, right? Now I realize that the furan is formed and then the side product is carbon monoxide. Very important to note. Now for this synthetic pathway, we have to take note of the materials and the reagents and the conditions. Very important, right? We cannot do without them. Now, pyrrole. We are saying that pyrrole commercially from is gotten from coal tar or by treatment of furan with ammonia over alumina catalyst at 400 degrees Celsius. So if we have furan, we can get pyrrole by adding ammonia and then alumina and then heating it to 400 degrees Celsius, right? Good. Now in the same vein, you also reason that we can also take it from the pentose mixture to the pyrrole, and these are the steps that we'll go through. Very simple and familiar steps. Once again, we are supposed to take note of the starting materials, the reagents, and the conditions. Very important. Now, thiophene. Thiophene can also be gotten from coal tar or by cyclization of butane or butadiene with sulfur. So what we have here is 1,3-butadiene in the presence of sulfur, and then we heat it to 600 degrees Celsius, and then we have our thiophene. And then the side product is H2S, right? Good, very simple. Now, unusual reactivity. So pyrrole is an amine in a very weak base. We say it's a very weak base because if it's supposed to act as a base, we have already mentioned that it would destroy the aromaticity, which we don't want to happen, right? Now, pyrrole, furan, thiophene are conjugated dienes, but they undergo electrophilic substitution rather than addition. Now, this is very common for all aromatic compounds, the stable ones, because the addition will destroy the aromaticity, so they want to undergo substitution necessarily, right? Yes, so that's for that. So we are talking about structures. Yes, so structures of pyrrole, furan, and then thiophene. So pyrrole, furan, and thiophene are aromatic. Yes. So all the properties we have talked about respect to aromatic compound will come into play here. Yes. Now, that's the same thing we are talking about. Cyclic. Now, it should be conjugated. Before conjugation should happen, each of the atoms in the ring should be sp2 hybridized, so much so that they can get on hybridized p orbitals, which will be perpendicular to the plane. The unhybridized p orbitals will overlap to form a molecular orbital, which will be flat, right? Now, that conjugated molecular orbital will allow the electrons to move freely. That is the delocalization that we talk about, right? So that is basically what we are talking about here, respect to conjugation or aromaticity, right? Good. Now, typical reactions they undergo. Typical reactions they undergo. So, bromination, they are saying that heterocycles are more reactive than benzene. And so you realize that compared to benzene, the conditions these ones are being subjected to is very mild. Now, if you want benzene to undergo bromination, you need the bromine, but you also need a catalyst, right? Chlorination is the same thing. You need a catalyst. You need the lowest aluminum catalyst or maybe a lowest acid to what catalyze the reaction. But that is not what you need in this case because these are reactive. We can do without them, right? So the first reaction is showing us bromination of furan to form 2-bromofuran. The next one is showing us nitration of pyrrole to form 2-nitropyrrole. The last one is Friedel-Crafts acylation of thiophene to form 2-acetylthiophene. Now, in all these reactions, you have to take note of the starting materials and the reagents and the products. Very simple. Good. Now, one characteristic thing that occurred here is that for each of the substitution that we had, the substitution occurred on position 2. On position 2. And so why is the substitution occurring on position 2? The reason is this one, that there's a carbocation formed or there's a cation intermediate formed. Now, if the substitution occurs at position 2, we produce more resonance structures. With the first one here, is showing more. We have 3 different resonance structures, right? Now, if it occurs at any other position like position 3, we have just 2 resonance structures. And so we have a concept that says that the more the resonance structure, the more stable the intermediate. Now, I've always said that reaction proceeds to form more stable products or intermediate. If the intermediate is highly unstable, the reaction will not go to that direction. So because we are producing more resonance structures here, which implies a higher level of stability, right? A high level of stability, it would undergo that. So we undergo C because we get more stable intermediates. Then why we know it's more stable intermediate because it has more resonance structures. Very important. Now, chemistry is practice. We have to be able to draw the resonance structure, and we can only draw them if we rehearse and practice them, right? Very important. Next up. So, electronic structure of pyridine. Now, this slide would talk to us about the basicity. So we are saying pyridine is stronger base than pyrrole. We've talked about that, but a weaker base than alkyl amines as a normal amines, right? Now we are explaining that the sp2 hybridized N holds the lone pair electrons more tightly than the sp3 hybridized nitrogen in an alkyl amine. So this is something that is very basic. I've already explained this, so we'll not talk more about it. But we have to take note of this order. That we have compared the basicity of pyrrolidinium anion, pyridinium anion, and then pyrrolidinium ion, right? So we have pyrrolinium, pyridinium, and pyrrolidinium, right? And then in terms of basicity, in increase on order, it starts from the pyrrole to the pyridine, then it goes to the pyrrolidine. Now, it follows the same rule. The first one from your extreme right, this one, right? It's a derivative from pyrrole, and pyrrole is very weak. That is why it has a very small pK, right? Very weak. Yes, very weak. Now the pK understanding is inverted, so we can just look at the basicity. So in terms of basicity, pyrrole is like the weakest, you understand, because when it acts as a base, it destroys the aromaticity, followed by pyridine. I've explained why pyridine is weaker compared to the normal one. The last one, the pyridinium, is not aromatic. It's a normal cyclic compound, right? It's a cyclo heterocyclic compound. It's not aromatic, and so and then the nitrogen there is sp3, just as we have talked about. So it doesn't really have a lot of the limitation that we have mentioned. So it's like the normal imine, right, in the pyrrolidine. Now, the pyridine ring undergoes electrophilic aromatic substitution reaction with great difficulty under drastic condition. Nitrogen is more electron withdrawing and decrease the electron density in the ring. Now, this is an important point that we have to take note of because it would resonate as far as we are talking about pyridine in terms of reaction. What we have done so far was talking about the 5-membered rings in terms of their reaction. Now we have come to the 6-membered heterocycle, and then the yardstick that we are using here is pyridine, right? Pyridine. Now we are saying that pyridine will undergo electrophilic reaction, substitution reaction with difficulty, right? Now the idea is that the nitrogen there has deactivated the ring because it's highly electron withdrawing. Now we can still make it undergo reaction under drastic conditions. So you see bromination occurs at 300 degrees Celsius, and more like the other one that we saw. Now we can still do sulfonation, we can still do nitration, right? But all of them will be under drastic conditions, very drastic conditions. And then you realize that the substitution is occurring at position 3. At position 3, the substitution is occurring at position, and there's a reason why it's occurring at position 3. Now, the reason why pyridine will behave in that regard is explained by these 3 mechanisms. Now, the first one is explaining the case where we have pyridine having a substitution, electrophilic substitution at position 3. We would have 3 different resonance structures, which are all accurate and applicable. The second scenario is when we have electrophilic substitution at position 4. Now, the resonance structure should occur to stabilize the structure. Let's follow carefully. Now, during the second course of the resonance structure, you realize that the positive sign has fallen on the nitrogen. Now, because the positive sign has fallen on the nitrogen itself is already electropositive because the nitrogen there, no, it's electronegative, highly electronegative, because the nitrogen there was pulling electrons, right? It's pulling electrons. So the nitrogen is pulling electrons from the ring, and then a positive charge has landed on it. So it makes the structure highly unstable. So this is not considered as a resonance structure. That is why it has the sign. This is not considered as a resonance structure. Highly electronegative nitrogen, and then we have put a positive sign on it, right? And so this is not considered. And so in essence, this one has just 2 resonance structures. Now the same case will occur for the 2 substitution at position 2. You will still have the positive charge landing here. And then when it does that, when the positive charge lands there, that part or that structure is not a resonance structure. So this is also not a resonance structure. And so you have just 2 resonance structures. So you realize that compared to the others, it is just the position 3 substitution that will have 3 resonance structures. So the number of resonance structures here will favor this one, right? Now, drawing it will just give you 3 resonance structures for all of them. But the truth is that if the positive sign falls on the nitrogen, because the nitrogen is highly electronegative, the word is electronegative, right? It will make that structure highly unstable, and then it cannot function as a resonance structure. I hope we are following. So that is the explanation with respect to the mechanism, reason why we have the substitution for electrophiles occurring at position 3 for pyridine. And so there's an assignment here which is just around what I have just illustrated and explained in the other slide. So that is that for that. Now we have nucleophilic substitution of pyridine. So nucleophilic. Now we are seeing that 2 and 4 substituted halopyridines readily undergo nucleophilic aromatic substitution. This is very specific. 2,4 halopyridines. So 2,4 halopyridines. The starting material is a halopyridine, but then we are looking at the halogen at position 2 or position 4, not position 3 for nucleophilic, not position 3. Electrophilic is position 3, nucleophilic is position 2 or position 4. Now there should be a halogen at those positions already, right? Now the halogen will just make the carbon there or the atom there a little bit electropositive, right? So that the nucleophile can attack it. And so if I am supposed to explain this this is not the mechanism, but the chlorine here is more electronegative. It pulls this carbon. There's partial negative here. There's partial positive here. And this gives this one the chance, the ethoxide, the chance to attack this carbon because it's a nucleophile. It likes positive charge. So when it attacks this, the chlorine is a good leaving group. It goes away. That is it, right? That's the nucleophilic. And this is similar to even the reaction mechanism. The same thing here. The amine group here has negative charge, right? It's a nucleophile. And so it can attack the carbon here just because the chlorine here is electronegative and has pulled on it, right? And has pulled on it, right? And so attack it, and then the good living group will go away for the nucleophilic substitution to occur, right? And so that is that for this one. That is that for this one. Good. Now, fused ring heterocycle. So this is another discussion where we have, which we have come to fused rings. So we have examples like quinoline, isoquinoline, and indole, right? These are all fused rings. We have benzene and the heterocycle, right? Good. Now, quinolines and isoquinoline. So quinolines and isoquinolines have pyridine-like nitrogen atom and undergoes electrophilic substitution. Reaction is on the benzene ring rather than the pyridine. We already said that the pyridine ring would hardly undergo electrophilic substitution reaction because it is electron deficient. That is because the nitrogen here is deactivating the ring in a way, right? We have already mentioned that fact. And so in this case, where there's a benzene attached to the pyridine-like nitrogen, that ring does not even undergo the electrophilic substitution, but it is the benzene ring that undergoes it. Now, the position for this reaction is usually 2. Either it occurs at position 5 or position 8, right? But on the benzene ring. So in the first instance, when we are doing bromination, that is what has occurred. And then in the second instance, where we are doing nitration, is the same thing that has happened, right? Good. That is that for that one. Now, indole has a pyro-like nitrogen. Indole has pyrrole bonded to benzene, right? So it has a pyro-like nitrogen. Now, pyrrole is electron rich. We've talked about it. It easily undergoes electrophilic reaction. And so you realize that now in bromination, we don't have to give it any drastic condition. It's just bromine, and the temperature is even 0 degrees Celsius, but it will still brominate, and it brominates on the electron-rich pyrrole. So this clearly shows you the difference between pyridine and pyrrole, right? Yes, so that is for how these two compounds will behave. We have to take note of how these two compounds behave. Now, examples of heterocyclic drugs, we've mentioned some of them already. Metronidazole, celecoxib, we have to take note of them and their uses. Sugar, right? Oxygen-containing heterocycles. Now, the subtopic is interconvention between alpha and beta forms of sugar. Now, this mutual rotation principle is a different concept, but it has come here, so we can just talk about it. The sugar alpha and beta. This is a chair conformer. We say it is alpha if the anomeric carbon, the OH on the anomeric carbon is let's trans to the CH2OH here, right? Now that is alpha. If it's cis to it, that's if it's the same angle, then it's beta. It's very simple principle here that we are using, but that's not the discussion now. Examples to alpha and beta can occur in polysaccharides. So the cellulose has 1,4 beta and D-glucose polymer. So 1,4 linkage, right? Yes, and so amylose has 1,4 linkage alpha, right? So cellulose is 1,4 beta, amylose is 1,4 alpha. So these ones will all come into play. Now, more drugs, sitagliptin is an anti-diabetic, then it has heterocyclic rings, right? Now, the examples go on and on. Sildenafil, a very common and important drug, has heterocycle, right? Very important. Basic ring system. So these are very basic systems, but then you can find them in very complicated drugs, right? Yes, very simple. We can take note of the drug and their uses. Timolol, phenytoin, fluconazole, losartan, they are all important drugs which have heterocycles in them. So this brings us to the end of the first slide on heterocycles. As I said, if you have any question, you can contact any member of the HESA academic board. Thank you very much and all of the best.